Hey, welcome back. Today's lesson is on exponential growth and decay. Now, all exponential functions, we're going to look at a lot of them today. They all come in the same form. We have two numbers and one of them is being raised to an exponent. So if the variable is not in the exponents, then it is not an exponential function. That x has to be an exponent. Hence, exponential function. Okay, so the first number that we have, we call the initial value, and that can't be 0. That's our first condition. And the number that's being raised to a power, that's called the growth factor or the decay factor. It's what you multiply by. So as x increases, you can see that we're going to multiply by b. If x equals 1, we have 1b. If x equals 2, we're going to have b times b. It's going to be a times b squared. So that's a times b times b. If x equals 3, it's a times b times b times b. So you can see that you're just multiplying by b each time. And that's why it's called the growth factor. Or if it's getting smaller, we call it a decay factor. Now, b has to be not equal to 1. That's the only, it has to be positive, it has to be not equal to 1. Those are the two requirements. If b equals 1, then you're just multiplying by 1, and your function's pretty boring. All right, so if it's greater than 1, we call it growth. And if it's less than 1, but it has to be positive, it has to be greater than 0, then we call it decay. All right, so let's look at the differences between exponential functions and linear functions. We know linear functions. Here's the line y equals 2x. Notice how, for every increment of x that you increase, you add 2. So this is adding 2, adding 2, adding 2. And that creates a linear function. All right, this is linear. Because you add the same amount every time, it creates a line. But if you start multiplying, this is 2 to the x. So when x equals 0, remember anything to the 0 power is 1. So you can say the 0, 1. And a lot of exponential functions go through 0, 1 because they're in this form. And when you raise it to the x power, if x is 0, you get 1. I mean, wow. Okay. But let's look at the function if this value right here, the growth factor, is not equal to a positive number greater than 1. What if it's a decimal or a fraction? Notice what happens to the curve. So this here is a growth function, growth. However, when that growth factor decay is less than 1, we get a decay function. And notice the decay function comes down and it levels out eventually. And we'll talk more about the graph later. So let's go through these different examples and see if we can figure out what the a value is. Let's look, f of x. I'm going to write it right here. This is what we're looking at. So it's ab to the x power. So let's see if we can figure out what the a value is, what the b factor, or what the b value is, and whether it's growth or decay. Okay, so the first example we have, we graphed it up here. A, is it exponential first? Yes, it is. That's definitely exponential. The a value, what number is in front there that we're not writing? A is equal to 1. And that one, this is really this. 1 times 2 to the x. And so the growth factor would be 2. And it's growth, not decay, because it's greater than 1. Easy enough? How about the next one? We have x to the negative 2 power. Well, for exponential functions, x has to be positive. So this is not exponential. So this stuff doesn't make sense. Next example. We have 4 times 0.1 to the negative x. Let me rewrite that over here. So we have 4 times 0.1 to the negative x. Well, I'm going to use our exponent rules, which I know you guys all love because you just passed a mastery check, right? This is 4 times 0.01. Instead of negative x, I'm going to rewrite it like this. I'm going to take that negative 1 out and make that x positive. So all exponential functions have to be written so that the x is positive. Now, if I take, this is really 1/10, and I raise it to the negative 1 power, I get 10. So I've rewritten that. Just put this in your calculator, and you'll get 10. So this is 4 times 10 to the x when I rewrite it. So this is exponential, yes. It's just written in a different way. A equals 4, and b is going to equal 10 here. And because b is greater than 1, it's growth. All right, how about the next one? 2. All right, what do we got? 2. That's the value of a. B equals 0.5. That means it's a decay function. Yes, this is in the proper form. All right, how about the next one? We have x in front. X is the value of a. That's the variable that's changing. So this is not exponential. Remember, the exponent has to be the variable. And right here we have a 5. So no, that's not one. All right, why don't you try the last two by yourself? Go, pause the video. Okay, back we are. Here we go, the first example here. Is it exponential? Yes, it is, because what do we get here? A is 10, and we have to work it out. So this is where the work is for that. I came back. So that's 6 to the negative x. Well, negative x, I rewrote it. Okay, it's 6 to the negative 1, and that's raised to the x. And then 6 to the negative 1 is 1/6. So this is exponential, and a is 10, and b is 1/6. It's a decay function. For the last example, you notice that b is negative and b must be positive, so that is not exponential. All right, so now we're going to look at creating equations to match the scenario. So we're just going to make sure that our equations are in the form of ab to the x. We have an initial value and then a growth factor. So the first example, a local college has increased its number of graduates by a factor of 1.045. All right, so that tells you right there, that's the growth factor. So that's going to be what b is equal to. Right there. All right. In 1997, 924 students graduated. So this is the initial value. So let's write it. So f of x, we're going to use our function notation, equals, we start with our initial value, multiply it by our growth factor, and raise it to the x power. And we're done. There's the equation there. How many students will graduate in the year 2005? Well, to get that answer, we're just going to plug in. Well, we're not plugging in 2005 because this is every year since 1997. So how many years has that been? That's been what? 1, 2, 3, and then 8 total. Okay, so we're going to plug in. X is going to equal 8 here. And we're going to plug that into our equation. So f of 8 is going to equal 924 times 1.045 raised to the 8th power. When I work that out, I get 1,314. So that is our answer to the last part. F of 8 equals 1,314 students, approximately. And of course, because there's a decimal, you can't have a 0.02, so we're going to round that. All right, next one. Sully's Dance School currently has 520 members. That is going to be our initial value right there. So that's what A is. Every day, 1/4 of them quit. So I'm going to write, what do we got here? So f of x is going to equal 520. And then every day, 1/4 of them quit. So we have to be careful here. I don't want 1/4 of 520. I want to see how many are left. That's what this function is asking, like how many are left. So if you take a fourth away, that leaves 3/4. Sometimes we got to be tricky there. We got to be careful, right? If 1/4 quit, then 3/4 are left. And we're going to raise that to the x power. So how many students will there be at the end of 1 week? And because this is in days, that means I'm going to plug in. We want to find here, let's change color. All right, so f of 7 is going to equal our initial value, 520, times 3/4 to the 7th power. That's going to be our exponential function. You can see as we work that out, make sure that you use parentheses in your calculator. And all of that will equal 69.4 students. So we'll just leave it at 69 students. We're going to round that. Okay, on to the last one on this page. Now this one's a little bit different because they don't really just come out and tell you A and B. What they tell you is that in 4 days, the population of fruit flies, which is currently at 150, it increases to 400. So looking at our function, let's just write our function out. So f of x equals ab to the x. What do we know here? We know that in 4 days, so if I plug a 4 in, so f of 4 will equal 400. So let's write that down. 400 will equal, if I plug a 4 in. Now, I also know that 150 is the initial value. So really, we're just stuck with finding for the value of b. We don't know what the value of b is. So if I divide both sides by 150, let's do that in this equation. And then we get, what do we get here? That reduces to 8/3. Is that right? I do that right? So 8/3 is going to equal, they're going to cancel b to the 4th. So how do we solve that equation? you can do it either one of two ways. You can raise it to the fourth power or take a fourth root. I'm just going to raise that to the fourth power. So b to the fourth to the 1/4 power. And that'll get those exponents to equal 1 when we multiply, right? So b to the first, kind of ran out of room here, is going to equal 8/3 to the 1/4 power. Got to work that out. And you can see down here, we got 400 divided by 150. Put it into a fraction, and then we raise that to the 1/4 power. I get 1.27. I'm going to call it 1.28. We're going to round a little bit. So b equals 1. Ooh, I want to be drawing right now. What's going on? So 1.28 is the value of b. Now, how many fruit flies will there be at the end of 1 week? Well, first let's write our function out, because we never really did that. Our function is going to be f of x is going to equal, we have the initial value of 150, which they told us, and we figured out that b was 1.28. That's raised to the x power. So what do you get when you plug what do we want to plug in? 1 week? And we're talking about days. So that is 7 days. So we want to find f of 7 here. So f of 7 is going to equal 150 times 1.28 to the 7th power. Let's work that out. So when I plug it into the calculator, you can see how I did that over here. I get f of 7. I am running out of room here, aren't I? F of 7 equals, about 844 fruit flies. Wow. Those fruit flies, they're crazy around here. They're crazy. All right, next question. One of the most useful applications of exponential equations are doubling and half-life formulas. So go ahead and pause the video and write these down. We have the doubling formula here on the left, doubling, and the half-life. And you can tell the difference. Ooh, I wrote half-half. What up with that? This is half-life. And you can tell the difference based on the growth or decay factor. So where there's a 2, obviously that's the doubling. And if it's a half, it's a half-life. Now, if you notice, the form changed a little bit because our exponent became t over x. Well, x here is the doubling. It's the time it takes to double. So I'm going to write time to double. Or we call that the half-life. If we're doing a half-life problem, it's the time it takes something to decay to half of whatever you started with. Now let's see how it works with the first example here. There are 500 grams of radioactive material. Its half-life is 5,700 years. This is how they figure out how old stuff is, by the way. You should know that. Take chemistry. You taking chemistry? Anyways, so let's write this. F of t, we're change it up. So our time is t here. It's going to equal, we're starting with 500 grams. So that's our initial value. And we're doing a half-life problem, and the half-life is 5,700 years. So that is what goes on the bottom. So we're going to write that, 5,700. And they want to know how many grams will there be in 20,000 years. So we're going to find f of 20,000. That's going to equal 500, 1/2 to the 20,000 over 5,700. And when I plug these in, just to make sure I always put it in the right place, I ask myself, that's about 4 half-lives, right? 20,000, because a half-life is about 5,000 years. So when I write my fraction, make sure that you're putting the bigger number on top so that you get about 4. Let's put that in the calculator. So when I plug that in, I get 43.92. So f of 20,000 is going to equal 43.9. I'm going to round that up. 93 years. No, not years. Grams. Right, because we're figuring out how many grams are going to be left. Goodness gracious. You got to answer the question they're giving you. How many grams will there be in 20,000 years? All right, why don't you try the next one? Pause the video, do the next one by yourself. Go. Okay, so did you figure this out? We have years and months in this problem, and they're telling you it doubles every 6 months. So this problem has to be in months. So 5 years is 60 months. So we're going to use 60 here. You got to put 60 over 6. And then you figure it out, you get 512,000 rodents. Whew, Mr. Bean's house. It is in the forest. In the forest. All right, so now let's look at what these look like on a graph. All right, we have our two different types, growth and decay. If b is greater than 1, that's a growth function, then the graph will grow away from the asymptote as you move left and right. Okay, we'll see what that means here in a second. If b is less than 1, or if it's a decay function, it'll grow towards the asymptote. And we put that into quotes because growing towards something means it's approaching it. An asymptote, okay, this is an imaginary line that the graph approaches more and more closely, but it never really crosses it. So let's look at these functions here, see if we can figure out whether they're growth or decay. And sometimes it's opposite of what you might think. Like with the first, well, let's go to the first one here. Now, do you see how the numbers, we start and there's slow movement. The numbers don't really move a lot. But then as x increases, these things start to shoot down. They're going crazy. They're going down quickly. Okay, this one here is a growth function. Now, a lot of students think it's decay because it's going down, but it's not. This is actually growth. It's growing away. Think of it like something growing into the ground. The roots are growing down. It's going away from the x-axis. This x-axis right here, y equals 0, that is the asymptote. So we're going to actually draw that for each one of ours. We're drawing the asymptote. This is y equals 0. And so this function approaches y equals 0 as you go left, but as you go right, it grows straight down. All right, let's look at the next example. We have another asymptote here at y equals 0 again. Now, is this growing away from it, or is it growing towards it? Well, this is growing towards. See how it's getting closer and closer? The values are changing more slowly, more slowly, more slowly, more slowly. This is a decay function. All right, so that's the difference between the two. Pause the video, do the next two by yourself. Go. Pause the video. All right, so what did you get? Do you notice how this function here is getting closer and closer to the line, but it's not going to cross? It's not growing away from it. That means this is a decay function. And make sure you label that asymptote. This is y equals 2. It's the line y equals 2 straight across. That is the asymptote. For the last one, the asymptote's at y equals -2. We can see that, but notice how the function's going away from it. That would be a growth function. All right, so now we know what they're supposed to look like. We can actually put them on a graph. So graph f of x equals 3 times 2 to the x. Here's how I graph the exponential functions. What I do is I try to make that exponent a 0, and then we're going to build a table of values. And if we know what it looks like, and we have a couple points, we can draw the function. It doesn't take too much work here. So I know that if x equals 0, my exponent here will be a 0. So I'll get 3 times 2 to the 0 power. All right, anything to the 0 power is 1. So that's just 3 times 1. That equals 3. So I start this graph at 0, 3. Okay? Now, the next thing I do is I use values around 0. So I'll go up to 1. It looks like we're just building a table off of guessing and checking. And really, that's kind of what we're doing. So I plug a 1 in. So what is 3 times 2 to the first power? Well, that's 3 times 2. 3 times 2 is 6. Okay, so at 1, we're at 6. So 1, 2, 3, 4, 5, 6. We're up here. Now, I might even go backwards. I want to know what this point is, so I'm going to plug in a -1. Okay, when I plug in a -1, I get 3 times 2 to the -1 power. Let me do that over here. 3 times 2 to the -1 power. You can do it in your calculator if you want to, but that's the same as 3. Remember a negative exponent? 1 over 2 to the positive. That's going to equal 3 halves, or 1.5. So for -1, I get 1.5. That's right about here. All right, I have 3 points. 3 points is enough. I'm going to draw the line so it looks nice, and it's got to be curvy here. What are we doing? Now, which points can you pick for your table? You really can pick any points for your table, but what I want to focus on is making that exponent a 0 first, and then I pick points around that. The domain of this, well, let's talk about domain. Where does this go? This is going to go up forever, and is it going to ever... Can we plug in any x value here? Can we plug a 10 in? Yes, we can. It'll be a super high number, but we can plug a 10 in. We can plug 100 in. Can we plug negative numbers in? Yes. Notice how all of the x values get used here. So the domain here, all real numbers. What about the range? Well, we have an asymptote at y equals 0. So we need to plot that on our graph. Let's do that. Y equals 0 is our asymptote. And so our range is going to be, it always gets closer to 0, but it never gets there. It never quite gets there. It's always closer and closer as you're moving left. So the range here, f of x. I was going to write y there for a second. It's the same, f of x. So f of x has to be greater than 0. All right, and this is a growth function because it's going up. Let's do another one. Number 2, we're going to make our little table here. I left you some space. So we got f of x is equal to -6, 1/3 to the x. I'm just going to start, remember, I want to make that a 0. So let's start at x equals 0. If x equals 0, this whole thing turns into a 1. So f of x is going to equal -6. All right, let me plug in a 1 now. If I plug a 1 in, then I get -6, 1/3 to the first power is 1/3. So -6 to the 1/3 power is -2. All right, let me plug in a -1. This one's always a little tricky. So -6, 1/3 to the -1 power. And -1 exponent flips. It's the reciprocal of this. It's going to move this 3 up to the top. So that's really -6 times 3, which is -18. All right, now that's going to be way off my graph. So let me go 1. So see, I'm just picking values here. Let me go to 2 because that's off my graph. So if I plug a 2 in, I get -6. Sometimes I'm going to work it out over here. Times 1/3 squared. That's going to be -6 times 1/9, which equals -6/9, which is -2/3. Okay, so it's a decimal, but that's okay. So we start at 0, -6. 1, 2, 3, 4, 5, 6. This is where we're at. 1, -2. Plot the points. -1, 18, -18. That's way off. That's like way down here. So you can see the shape of this. It's going to come up. 2, we're going to be at -2/3, which is right about there. So this function kind of looks like this. And it's going to go down. Notice how it's a decay function. The growth factor here, decay factor is 1/3. So it's decaying. It's getting closer to our asymptote. We should write that down, which is y equals 0 is our asymptote. So this is a decay function. The domain here, once again, it's all real numbers because all the x values get used. And the range is f of x has to be less than 0 in this because it's going down. So the function is less than 0. All right, one more to do. This is as hard as it gets right here. All right, so we're going to build our xy table here, or x f of x. Remember, f of x is just y. It's the same as y, so don't let that bother you. And as I said, we want to make that exponent 0. So this one's a little different because, look, we have x plus 4 up there. It's kind of ugly. So how would I make that into a 0? What if I had x equal to -4? If I plug in x equals -4 in up here, what do I get? So -4, that turns into a 1. Right? This whole thing would turn into a 1 right there. And I'd get -2 times 1 plus 3. So that's just -2 plus 3, which is 1. Right? Plugging it in. Next one. Now I'm going to pick values around -4. So how about -3? So if I pick a -3, I'm going to get -2, 3/2 to the first power, right? Plus 3. So if I work this out, this will equal -3 plus 3. That's a 0. Let's plug in a -2. I'm going to erase that for now so we can stay focused. If I plug in a -2, I get -2 to the 3/2 squared, and then I get plus 3. So this equals -2 to the 9/4. Yeah, we're starting to get decimals, and that's going to happen. Plus 3. Let's just break out our calculator. All right, when I break out my calculator, I get -1.5. All right, spoiler alert. We can use our calculator a lot more than we have been. Let's go to y equals. Clear out everything in y equals, shall we? Let's put in this function right here. So we get negative 2 in parentheses. We have 3 halves. And we're going to raise that to the x plus 4. And then we're adding 3. Now, zoom 6. We'll put you in a standard window, and that's what our graph looks like. So first, is it growth or decay? It's obviously growth because it's going down. Okay? Let's go to the table of values. Now, because we're smart kids, we know that when x is negative 4, we should get a 1. So I'm going to scroll up to negative 4. Notice how we get a 1. All right, a 3. Negative 3, we get 0. Negative 2, we get 1.5. Look, we have all these values right here. So can you use your calculator? Absolutely, I'm okay with it. Just make sure that when we plot our graph, we're plotting actual points. We're not just drawing a line on there. I know some of you students that would do that. Okay, so negative 4, 1, 2, 3, 4. Negative 4, 1. Negative 3, 0. Negative 2, negative 1.5. So we get a graph that looks like this. Now, notice that plus 3. That took our asymptote, which is normally it's grounded at y equals 0. It moved it up 3. That's kind of hard to tell on this graph. All right, so we put in our asymptote here at y equals 3. This graph is going down, and it's coming up like this, closer to the asymptote. So this is a growth function because it's going away from the asymptote. The domain here, all real numbers, right? Because we can use all the x numbers. In the range, well, look, this range is a little different. So f of x, which is like y has got to be less than 3. So we're going to write f of x equals less than 3. So can you use your calculator? Absolutely. As I said, like I'm okay with using your calculator. If you want to get some more points here, do we want to double check the asymptote? Make sure it's y equals 3. We can scroll up. Let's check it out. When we scroll up, we're going super far left on the graph, and check that out. The asymptote turns into a 3. Now, your calculator says 3, but it's not really 3. It's actually getting so close to 3 that it rounds it up to 3. All right, so here are the steps. Build a t-table for x and f of x. Start at the value of x that creates an exponent equal to 0. Fill in the table. You can use your calculator to help you there, and then don't forget to label the asymptote. And that's it. There's exponential growth and decay functions. A lot of stuff here, but I don't think it's too difficult. If you have any trouble, please ask your teacher. This is Mr. Kelly in K-Town. Remember, it's nice to be important, more important to be nice. See you.